Okay, we are live. Can you lower the volume on that so there's no feedback? Great. It's audio. Okay, great. I'm going to share my screen, and it's just going to be screen share. Great. Howdy, everyone. This is Stephen Mendelson.
Dean Patton.
And we're going to do a quick little informal tutorial on how to do internal flow on an ANSYS, like we're doing on the injector, but like on any kind of fluid through a pipe kind of deal. We're only going to deal with getting mass flow rate, velocity, and pressure data given pressures, but you can give it other boundary conditions. So you'll want to open up your workbench like usual. As far as the CAD file, we're using a SolidWorks assembly file. And from there, we're going to create an internal volume to that of where the fluid is going to flow. So you can have your whole system as a solid, and then you can extract it and make a new, basically, we're gonna make a new part file from this if it won't act up. But yeah, so yeah, we're gonna give it two pressures, which based on if you look it up, you can find out if you're gonna get a unique solution or not. If you have two pressures, you can get a unique solution. So we have the inlet pressure as 150 psi. This is for the water test stand, and the outlet pressure will be 1 atmosphere, obviously. And yeah, so let's start up. Great. Great. Oh. Okay. This condensing on the side, you can actually fix it. We're not going to, because I don't want to need to do it live, but the way you fix it is you go into like the properties of, you go to the like ANSYS workbench, you right click it, you hit properties, and you go into the visual thing. If you look up this problem, it's a very common problem to have. You fix it once and it never happens again. But yeah, we're gonna pick ANSYS Fluent Flow. We're gonna put it here, and we're gonna start with the geometry. And we're going to import the geometry. We're gonna pick, I'm gonna do taller or wider?
Let's do the taller.
This was a beautiful little CAD file made by Cheyenne from the injector team. Okay, so now you're gonna open up, you're gonna hit edit in space claim. What we're gonna do, like I said, is we're gonna create basically a border of volume, and we're gonna extract that as the only item we're gonna deal with. Yeah, it makes sense. So yeah, it's gonna launch a new application called Space Claim, which is just a CADing thing. It's like a worse SolidWorks, basically. Fair, yeah. Yeah. Great. Let's make this full screen. It'll take a second. This whole process, a lot of it will be waiting. That's just kind of the nature of running this kind of program. You can kind of see your status over here in the bottom left of any program. It shows kind of what it's doing. If you're waiting, it's like when you're running your simulations, it will show you what iteration you're on and whatnot. So here you go. Here's the full injector. It should look familiar if you're near the recording date of this video. And what we want is we're going to do it through the oxidizer way, because there's two fluids flowing through this injector, propane from the side and the oxidizer on the top. And you can't do them at the same time because it's two different things. So we're going to do it through the oxidizer channel. So the very first thing you want to do is you're going to go into prepare, which is this kind of, this top thing, and you're going to hit volume extract, like I said, and we're going to pick all the surfaces that we're going to send fluid through. So our first one is this. Wait, shouldn't it be? Oh wait, it should be edges. So let me just try it again. Go there. Yeah. So you're gonna pick this one on the right here. This is just allowing you to select edges of it, and it's gonna create a closed loop for you. And then we're gonna return this to the bottom, and it should be all the pink holes or all the lighter holes. We're gonna pick the edges there as well. And I'm holding down Control and clicking all these edges. This warning is kind of annoying. It's not important at all. Just have to go around it. I think it's blocking one of my holes. Yeah. Oh, don't forget the middle hole. That's really hard to click. Okay, great. So now we're done with that. We're hit check mark. And what it's going to do is it now has created a geometry, like I said, inside of there. And the final thing we have to do in space claim, you can kind of see the geometry right here, but we're going to disable all the other ones. So we're going to suppress it for physics. And then we're just going to hide them. I think we can just delete it, right? Oh, great. Okay. So now we have this volume. This is where the fluid is going to flow, and we forgot a channel. Okay. That is so embarrassing. Okay, so when this happens, I think you can just restart. So yeah, that is so annoying. But at least we're showing you real problems. If you need to skip this to where, if you did it correctly and you didn't miss a hole, you can skip to when we start meshing. Okay, so we're gonna edit the geometry in space claim. That is so frustrating. How you just restart the whole thing, you think? Or
Probably. I would
okay,
think so.
we'll try it again in space claim and see if it all showed up again. I could have probably hit Control Z. That probably would have been smart.
Yeah.
That's what you're here for, to help make sure I don't be stupid.
That process though would be the same if we were doing the fuel side though. You would just select the one on the side and do the same process.
Yeah, the important thing is make sure your holes. It won't let you make a volume otherwise. Okay, so if I hit Control Z. Yeah, it's giving me that noise. Okay, so yeah, we're gonna have to restart this. That's so annoying. But oh, can you pause the recording? But okay, as you can see, we selected all the holes. We've had a member of the engineering team, Colby, join us. We're gonna hit check. Like we said before, we're gonna suppress for physics all of these, and we're just gonna delete them. Great. So now we have, yeah, this looks right. This is basically the surface of the boundaries of where the fluid is going to flow. From here, we can just, we can just leave, just exit out. Colby, how's our audio, by the way?
Audio's good.
Great, thank you. Okay, now we're gonna go into mesh and we're gonna hit update, or that might not be yet. Actually, it says you hit update, and that's just gonna basically put the volume, all these new, the physics that we're suppressing, this new volume into our mesher so it can be prepared for us when we open it. Yeah. Awkward. Maybe you want to pause the recording while it's loading. Okay, yeah, just right click on mesh and then hit edit. And as you can see in the bottom here, it's kind of small, but it says, oh wait. Double click to edit. Is it being weird? Oh, there you go. Great. So now we're gonna hit edit. We're gonna refine the mesh. So it's gonna make one out of tetrahedrals, which is nice. That's the shape we're looking for. Because it's not a nicer geometry. It's not a simple geometry, I should say. And we're gonna give it certain mesh densities at different points, our most interesting points, the points of interest, I should say. Here we are. So first we're gonna generate, and it's gonna create, oh wait, you know what? we need to create the faces first. Right, yeah. Okay, great. So before this all happens, we're going to create some named areas. The first one's going to be our inlet. Sorry, let me slow down. I hit right click, I click left click on the inlet, and then I hit right click, and then I'm going to hit create named section. And this is where I name outlet, sorry, inlet. When you name them, actually, inlet, outlet, and walls, the program recognizes that you've named it that, and it will auto assign these name sections in our solution generator. You'll want to do that to the best of your ability to keep these names. I used a weird name one time, and I had to like dig through it to find it. So just use the right names if you can.
We're going to use these later for our boundary conditions when we actually run the simulation through it. So having those all named just makes it easier. I mean,
Yeah, you'll need that to be named. Why is this picking edges? Is that how it's supposed to be done? Oh, there we go. Great. Now pick all your outlet faces. Notice I'm not picking the whole little cylinder thingy or the edge. I'm picking the whole face like this. Just hold down Control, click all of them. Yeah, it's a little bit annoying. It's not as bad as the oxidizer one was a bit more annoying. Okay, great. And now we're gonna right click, create name section. This is gonna be outlets. But generally you'll want to name things together that are going to have the exact same properties. So like all the walls are going to have the same conditions and whatnot. What I'm doing here to click really fast is that I'm holding down left click and I'm just kind of dragging it over all these surfaces. Be very careful, be diligent. This is just kind of the most annoying part. Yeah. But you don't want to click the ones you've already named and whatnot, obviously. Also, don't forget the underneath of things. Made that error. And ultimately, if you do mess up, you can always do it again. Like I've spun this 100 times. Okay. Looking over, looks good. So we're gonna create name section. And we're gonna call this walls. Great. Now we have all of these. When we hit generate mesh, and then we hit mesh, it will show us our mesh. Really cool, right? The first thing you should notice is really dense here, not so dense here, really not so dense in the inlet. For this simulation, our goal was to get the max flow rate at the inlet to suffice our conditions so we could get that number to fluids. So what we wanted to do is make sure it's really accurate. And so we're gonna choose to create this surface right here, a higher mesh density. And so we're going to, what was it? We're gonna go to mesh and we're gonna hit insert. It was sizing, or was it contact sizing or refinement? Oh, I used refinement actually when I did it. You hit refinement and you just hit enter. Okay, selection. You hit apply on this one face, and then you hit generate, and you click on your mesh to look at it when it's done. See, it's loading with this red. It will just make it more refined. Oh, you can be more exact with it, obviously. I actually did it wrong. I need to put refinement. I put it up to 3, and I think it just makes it 3 times more dense. I could be wrong, but we hit mesh. Well, once this is done, and let's do it to our. We do it the whole stem, or did we do it just the end? Oh yeah, great. So now look, that's way more fine than it used to be, and that looks good enough for now. You can do the same thing for the outlets as well. These look really good for density wise, so we're not going to do that, but you could. And then we're less worried about these walls, these upper areas, so we're not going to do anything about it. So yeah, now we have our mesh. Everything's good here. We're going to hit close. And we're going to hit update. This one should be much faster than the last one, so we're not going to have to pause the video. I say that. maybe not. It didn't give me trouble when I did it on here. Dane thinks that the Arrow computers are faster.
They definitely are. You guys get the second hand.
We're currently in the CIC room, I think. Yeah. Creative and Collaboration Center or whatever. Okay, great. So check mark means done. Now we're gonna go into setup. You're gonna hit double precision. One's fine. You can also go into like give it how many GPUs you want to give it and whatnot. It's a bit more advanced than we're doing right now. This is just our basic internal flow simulation. There will be a class probably next semester, so spring 2024. Crazy, 2024 sounds like such a huge number. On internal, external flow, multi-fluid flow, parallel processing, all this stuff, and this should be well documented, hopefully in the red Google Drive. So, but this is just an introductory internal flow video. Give it a second. Great. Okay. So the next thing we're gonna do, don't worry about the arrows. I always worried about this one not having an arrow. Normally one of them doesn't have an arrow. First thing we're gonna do is we are going to go into materials. So it's automatically gonna want to run air, and the material is aluminum because that was what our part file had. So we don't want to use air. We don't want to use water. We're using liquid water at room temperature, so room temperature density and whatnot. So we're gonna add a new fluid, and it's gonna let you make one yourself. But we're gonna use a database because it has a lot of them here for us. Physically, it has water as a liquid, and so we're gonna copy it. You'll see it populate over here on the left. That's how you did it. Now you have water, but you can't get rid of air yet because your simulation still thinks that you're using air. So you need to go in and go to fluid, edit it, and you need to change it to your new liquid water. Once you apply that, it will let you delete air. It wouldn't let you do it before. So now we have liquid water running through aluminum, and this is in the right boundaries. So we're done with those. Next thing is our boundary conditions. This is the fancy stuff. Inlet, you can see it's already populated. We're gonna hit edit, and we're gonna see that it's expecting us to give a velocity and some data. We don't know the velocity. That wasn't given to us by the fluids team. Nothing wrong with that. But we're going to get we're gonna give it something different. And we're gonna give it a different type, pressure inlet. We're gonna give it, and we're gonna give it at pascals. We should have that written down. Do you want to pull up that Google Sheet? Here, pause the recording. Sorry, guys. Okay, we're back. So inlet PA is the inlet pascals. Inlet you see is 150 PSI. By the way, we'll talk about this whole spreadsheet in 1 second. It's the outlet PSI, PA in PSI. So this is 1 atmosphere. You can tell it's an order of magnitude lower than this one. Yeah, okay, great. So we're gonna just take 103 for 250. And we're gonna put in here 103 for 250. And we're gonna have 5% turbulence. This is all fine. This is standard. This is not a super high accuracy CFD. We could make it more accurate. We could have more the right turbulent. We could have the right supersonic, whatnot. But because this is water at 150 PSI, it's just not a super complex thing. When we run it for a real hot fire, it will definitely be more complex and need to be more accurate. That will be covered probably in that class. So now we've applied it. Great. Internal, don't need to really do anything about that because it's going to calculate its own volume it's going to run through. And then outlet will automatically switch to pressure when you give it an inlet pressure. I think I gave it the wrong number before, but 101,328. We're not going to be too exact. Great. And just for good practice, let's make sure this is right. Yeah, it looks right. Okay, great. Okay, great. Everything has been well populated. And now we're going to add in some of our monitors, which are things that we want to know. It's going to automatically be able to give you some data, but if you want like a generate a report, you can do that here. The first thing we want is a report plot. Make a new one. We're going to want MFR inlet, so mass flow rate to the inlet. It's gonna be new. It's gonna be a surface. Yeah, we're going through a surface. From the mass flow rate. So yeah, MFR inlet real. And it's me to the inlet, and we're gonna okay. And that's gonna generate us. It's been cool. I think that's all we're gonna do for now. Or do you want to get something else? Maybe pressure. Pressure should be the same. So yeah, let's just do this for now because this is the goal of when we ran the simulation to begin with was to get mass flow rate to later calculate the coefficient of discharge, which is a geometric property. So when we do change the mass flow rate or do change the pressures, that won't matter. It will give us the same number regardless. This is so we can test our real wet fire. And I'm on to two. Okay, great. So now we have a plot here for MFR inlet, and we're good to run our simulation. So we're gonna hit run calculation. It should change this. We're gonna run for this. We're only gonna run 100 iterations. We've been running 200 for all of ours. It should be approaching a normal number, approaching an expected number. For example, like our coefficient of discharge, we expected at 0.6 and 0.7, or around that area. And so that makes sense. Our mass flow rates, we were expecting a certain ratio, and we got that. You can always run more to be more exact. 100 iterations should be fine. And then we hit calculate. It will initialize itself. You'll see the console will have updating stuff, and then we'll start running iterations, and it will create you two graphs. And starting to run iterations, it will pop up a graph in a second. I'm pretty sure. Actually, no, this is not an iteration. This is the initialization. I'm pretty sure. That's way too fast anyway. Yeah, there we go. And it should start populating. Yep, calculating the solution. Should give us an iteration in a second. Yeah, there we go. So this is your updated plot, and so you can see 0.5615 is pretty close to expected. And there's now it's on 2 iterations. We will come back to the video after that. First, we'll talk about this spreadsheet. This is found in the injector CFD, whatever the water test stand drive folder is at the time of watching this, and you can find this calculator. Basically, this just finds coefficient of discharge given some initial conditions. And what we're trying to find right now is the mass flow rate. And so we tested different iterations to make sure that wouldn't be an issue, that the coefficient of discharge wasn't wacky. If it was wacky, we wouldn't have probably would have assumed the CFD is wrong. But we use that just to validate some assumptions. So we don't have to choose which geometry based on this result. We can base it on like how easy it is to machine or how well it interfaces with our design. And so yeah, we have mass flow rate for each of these, and then I plugged it in here to get our coefficient of discharge, and those numbers are displayed here. You can tell they're basically all the exact same. I think 0.9 is like a super rigid body, and like 0.1 is a super like straight flow. Is that correct? You can look up what the meanings of coefficient of discharge is, but these numbers was basically what we expected. Our team all seems satisfied with these numbers. And yeah, so this just uses the m dot over a being our outlet area. This is the conversion of PSI to Pascal. These are your PSIs. This is your density. All that goes into the calculator. This is just our different areas, so we know of our outlet, and these are all of our data. Let's see where our simulation's at. So yeah, let it run your iterations, take a break, do some other work, and we'll take a pause, and we'll come back. Howdy. Okay, for you, that was no time. For us, it was like 15 minutes of chit chat. Okay, we're done. So we're gonna go to our scale residuals. Yep, looks like everything approached a normal number. If this was kind of sporadic, you'd want to run more iterations. And it looks like our mass flow rate approached 0.6965. And I promise we didn't plan this, but that was the exact mass flow rate we got the last time we ran this for the proof number. So you can see here that iterations is important, but you can just, if we're talking about how like there's an AI that can assume the number and it's like extremely accurate. Anyway, so that's how you run one of these. Another cool thing you can do is you can get a contour or vectors So you want to do static pressure and you want to do it through all of these. You can save and display it. And it can give you where the pressure drop is. You can see it makes sense that it's across that big drop off area. That's the design anyway. And yeah, is there any, I mean, this is one atmosphere down here. Anything else you think we should show? We could do vectors too.
Yeah.
You know, we could show like velocity one is kind of cool, I think. Oh, they're really small. So oh wait, I need to pick a surface for it. Yeah, they're super small, so can't really see the magnitude very well. But I mean, it makes sense, right? It goes down and then it goes out and then it goes through these channels, and it's going to pick up velocity. Yeah, the whole thing. We're anticipating a pretty high velocity. We were looking at videos of what 150 psi looked like in a larger stream. Anyway, that is, yeah. So it looks like these are what, green, so it should be like pretty fast, I think. I don't know. But yeah, that is how you run an internal flow. Colby, anything to add or say?
No, I think we're all good.
Okay, well, thanks and gig 'em. And yeah.